gonna pick up on R3 conversation or 4 conversation?
Probably, maybe that's what I want to. See, but I need a mic. Hi, welcome.
Does this make you nervous?
No, not at all, but it's just awkward because I might have to watch it. But I think Luke's spot on where we need to like pan the crowd and like get some stock footage of learning going on.
You should do a point of view. You need a photographer.
Oh, I need a GoPro. I am actually getting into this, and if I can get this on Schoology, a GoPro might be the next step.
Sure you don't catch some things you don't want to see.
Okay, so Michaela says I have to screen record.
Press. Will it not work while
Yeah.
you're screen mirroring?
Guess we're gonna find out. We're gonna unmirror it. What if I record then mirror maybe?
Hack the system. Life hacks.
Like being smarter than
Life hacks when those are failed. That's actually serious.
stop mirroring. That's how you gotta do it. Okay.
Well, then we can't see your progress.
Oh, 3, 2, 1.
No? There you go.
Live, and I am live, and now I'm gonna go screen mirroring. AirPlay unable to connect. So I have to make a choice. So I think I'll just record it, and you just have to listen.
Sounds good. That's why you have to get a GoPro so that.
Wait, but why do you have to record what you're doing on
I really don't. Except that in my vision, I had this beautiful vision of me talking, and the notes going like split screen shot. Wouldn't that be cool?
Yeah.
Yeah.
Like on.
So it'd be like wah 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 wah, and then writing would appear.
How is there not a way to do that?
Amazing, isn't it? It's got to be something with the communications.
I think you can like turn on like pick up outside sound for
Yeah.
your screen recording,
That way you could hear you.
so that you can hear yourself talking and writing the notes.
But it's still not.
Yeah,
And then it would
like-
be
It's not gonna be
recording you
displayed
from
up
there,
here,
and you'd
but-
have to put the,
Which is still.
like, line above.
Hank, would you check and see if I'm on this? Am I covered?
Yep, you're in.
I'm in. All right.
You can't see the board though.
Well, that's okay because I'm gonna put.
Do you
the
want to
notes
focus? No.
there. You can't see the board.
No. Like you can't see what it writes.
Okay.
But it's just because it's not focusing.
Oh, so focus it.
Kind of.
Or do I need to like put it right in front of me here?
I think it's good.
Okay.
That's why you need a GoPro on the helmet. Like.
So then it would just like curl down and you could see like that.
Yeah.
Okay. All right, so I do want to talk to you just a bunch of differentiation rules. At this point, we should have a general idea that a derivative is a rule. It creates for you functions that give you slope for various points. Okay? I want to start it off with something that looks like this. Okay, let's draw a graph. And I'm going to draw like a piecewise function here. Let's see. We're going to go. That and that. And I'm going to call that f of x. That work? So it's a really weird deal. I mean, it's not a continuous function. Let me tell you this, some of the things that I do want to talk to you about today, and I've kind of got two things going on at once here. I want to talk about when is something differentiable, or in other words, when can we find the derivative, and I want to give you a whole bunch of shortcuts to find derivatives very, very quickly. Okay? So I'm trying to mesh two things here. And the other aspect with this derivative, and I'll keep coming back to it, is every time you find a derivative, what you are really doing is you are talking about slope of that curve at a specific point. Okay? So with that, from here to here, could you tell me the slope of that line?
Yes.
Yeah, what does it seem to be?
1.
1. So if I did tangent lines anywhere along those points, what would the slopes of the tangent lines be?
1.
1. They would be the same. So if I want to come back here and draw the derivative, I want to draw f prime. Okay, and remember that f prime is notation for derivative. And a lot of times let this be the guide of whether you want to call it f prime, y prime, ddx, or whatever. They called it f of x, so I'm probably going to work in f prime. Okay? So f prime, I'm hearing the slope of that is 1. Okay, well, at that point, there is no ability for me to have a point, and I am not differentiable where it is not continuous. So here's what this looks like. Open circle, straight line at 1, open circle. F prime does not exist at that discontinuous point. Does that work for you? Okay. The black line is going to be f prime. Right? Now, let's talk about the slope of f here. What are the slopes of the tangent lines there going to be? What is 0?
0.
So f prime is going to look like that. That work? Okay. I'm going to solid that in a little bit so that you can see. I might even just solid that in. Okay. And again, look at the connection. Okay. If I picked my x value as negative 1, 2, 3, 4, which is right there, the slope of that line at that point is 1, and the value of the derivative at that point is 1. Right here at negative 2, the slope at negative 2 of the function is 0. The value of the derivative at negative 2 is 0. And at any point in between there, really. Okay? How about from negative 1 to 1? What's our slope of that function?
Negative 1.
Negative 1. All right, so if I want to draw the derivative, it looks like this. Please note my open circles, because at those points I am not differentiable. Okay? And now from 1 to 4. Now the slope jumps to what? 2. Okay, cool. So from 1 to 4, my slopes are 2. And I'm going to note that my black line is f prime of x. Okay, and what I really, really want to tie into is this. The slope of that is represented by what the value of f prime is. Okay. Does that work? All right, let's talk about parent functions. Absolute value of x. What do absolute values look like?
A V.
Perfect v's. Okay, so let's move on to something like this. Let's say, okay, again, I'm trying to get you to get a graphical connection before we just start rolling out equations. Okay, so now I'm going to do, and that's going to be f of x, which equals the absolute value of x. Okay? So let's sketch the derivative. The derivative is going to tell us about the slopes of tangent lines. So let's take this from negative infinity up to 0. What is the slope of every tangent line from negative infinity? And we start thinking tangent, 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 tangent. What slopes are we looking at? Negative 1. Never changes, does it, until it hits 0. Okay, so let's go and we're going to look at our f prime is going to look like this. Now let's talk about this point right here. Right here where it changes directions. That's a dilemma. Is it? Is that really tangent though?
I don't know.
Remember what tangent allows you to do? Remember yesterday on Desmos when I was zooming in and it looked like that tangent line and the curve became the same line? Well, if I zoom in onto a tangent line at the point of the change of direction on the absolute value, you are not going to get the term that they would call local linearity. You're going to have a V and a line. In other words, no matter how you zoom in, that's what you're going to see. And you could keep getting closer and closer and closer, and they are not going to mesh. And that's why I need to tell you that the other place that derivatives don't exist, sharp turns. Anytime there is a sharp change of direction, you do not have a derivative being existing. So that means right here at this point, I'm going open circle. Because the derivative does not exist at 0. So there's two requirements of differentiability. Smooth and continuous, no sharp turns. And that's really the only two that we got to really be concerned with. I'm going to write that on here too for those that aren't here. But let's continue here. From 0 on to infinity, what will the slope of the tangent line be? 1. Okay. Open circle, on to infinity, and that green line is f prime of x. But what does f prime of x equal? Let's get an equation. Well, hey, what's the equation of that line? What is it? -1. So this is a piecewise function where we're -1 when x is less than 0. Okay. When x is greater than 0, what's the equation of our line? 1. When x is larger than 0. And again, I reference you back to this dilemma. I don't know whether it's filled in top or bottom. There's definitely a jump, but there's no smoothness. And one of the things that they would say is that you have to have a right-hand and left-hand derivative that are the same. That's not really a big AP calculus thing, so I'm not going to jump into it a little bit. But what they're saying is, as you're approaching a point from the left and you approach it from the right, if they have essentially the same derivative, then you have a derivative at that point. And here there is a definite, hard change in direction. So it does not exist.
So you just can't get the derivative at 0.
Correct.
At other ones you can. Like 2.
At every other point you can. Yeah. So like if we said, hey, here x is 2. There's the value of x of 2. The slope of the tangent at 2 is 1. Okay, because it's at 2, right? You got that. Okay? And there's f prime, and there's an equation. Am I making some sense? Does this kind of work okay? Right? And what's weird is that people see that out of context, and that's like one of the hardest things for them to deal with. They're like, I don't know how to deal with that. Well, visually, you should now. All right? Think parent functions. And again, why does AP Calculus want you to think about it graphically, numerically, and analytically? Because this stuff doesn't make sense if you only try to think about it one way. If you only try to do things analytically, you're losing 2/3 of the experience. Okay? But if you understand things visually and analytically, it starts locking together and making sense. Okay? So let me go under here and give you these two conditions. To be differentiable, and differentiable basically means for a derivative to exist. To be differentiable, you have to have two characteristics. Continuous now, I think this kind of leads to what Hank was talking about too. No sharp terms. That means the derivative exists everywhere else. It just doesn't exist where the sharp turn is. Okay, so this would be, maybe a better way would be to say to be differentiable at a point. Okay, so to be differentiable at a specific point, you have to be continuous. You can't have sharp turns. Okay, and I'll just note, f prime of 0 does not exist for f of x equal to absolute value of x, and then I'll draw that little point up there for the sharp turn. Okay? Good to go? Make some sense? All right, let's expand on this a little bit. And let's try this picture. All right, so I'm gonna put point A at 0, 1. I'm gonna put point B up there a little bit above 4. A little bit between there, so we're gonna put point B right about there. Point C right there. There's gonna be D. I'm gonna go with E right about there. We'll take F right about there. I might even throw a G out here. My curve that I'm working with is I'm gonna connect these. There. Sure.
So do you need to see the graph to know if it's differentiable?
It helps.
At the sharp turns?
Uh-huh, yeah, well, do you need to? No. If you do, you can see it right away, because sharp turns jump at you. But what are the only 2 times where sharp turns kind of come at you? One you just saw.
Absolute values.
Absolute values, okay. So right away, if you're like, oh, find the derivative of an absolute value, you're in your head thinking, at one point, this thing's not existing, wherever there's a sharp turn. And we know that absolute values can be upside down or here, they can get squinched there, or they can get widened out. But no matter where that V turn is, you're having a sharp turn. The other place where they can happen, piecewise functions. Because you could go from an x squared graph to suddenly a y equals x graph, and they could make them join up, and they're still continuous, right? So it meets the continuity, but there is a definite change. There's not a smooth transition to there. And so at that point, it would also not be differentiable. Okay, so really that's the only time. Almost all straight up polynomial functions are going to be differentiable. They all are. Okay? Rational functions where they have a denominator, they're not going to be differentiable anywhere there's a whole or an asymptote. So that kind of gives you an idea of, yeah, that's why we talk about asymptotes, continuity, all of those things in pre-calculus. Because where those things happen, calculus doesn't work, it fails. Okay? Okay, so from here, I want to just maybe sketch myself a picture of f prime. Based on these points A, B, C, D, E. I didn't label F, did I, for some reason? Okay. So based on these points, I would like to sketch an f prime. So we are going to sketch f prime of x based on A, B, C, D, E, F, and G. Okay, we'll do it in yellow. All right? Don't necessarily start with A, B, A, because there's some points that are really good to start with, like C. And remember what the derivative is going to do. F prime gives us the values of the tangent line slopes at those locations. So here's C.
0.
Tangent line of 0. Okay? And so I might do this. I'm going to just give myself a little tangent line right there. It's got a slope of 0. That means that f prime has to pass through 0. Make sense? Where else is the derivative 0? F. Okay, so straight down from F, the derivative graph has to pass through 0. Okay. Okay, now let's look at, yeah, go.
So A and G, oh, that's not differentiable, right?
Correct, it's not really. So we'll have open circles on either end. Okay, but it will give us an idea about where to start from. Some other questions before I get actual details. Tell me about the slopes of the tangents from A to C.
Positive.
Positive, right?
Bubble.
That means that the derivative graph from A to C is above the x-axis. That work? Tell me about the slopes of the tangents from C to F.
Negative.
Negative. the graph of the derivative is below the x-axis. A little bit of foreshadowing here. Can you now tell me if a function is increasing or decreasing based on the value of its derivative? If a derivative value is positive, the function is increasing. Right? And if the derivative value is negative, the function is decreasing. Okay? Foreshadowing, that's a bigger topic later. Okay? From f to g, what's true about the derivative? Positive. We've got positive tangent lines. Okay, so let's then do this. Let's take it in A. Give me an estimate, a numeric estimate or so for what you think the tangent line at A is. And if I were to draw that in, what's that?
Like
3-ish, I heard 4-ish.
5.
Okay, it's steep, is it not? Okay, I'm not going to be able to be perfectly accurate here because I don't know the equation, but it's fairly steep and positive, and as it moves here, what's happening to them? They're decreasing, they're getting smaller, yet they're still positive, right? Okay, so I'm going to do something like this. I might say, all right, I'm going to go up, I'll put it somewhere up here about there, and I'm going to call that A prime. Okay. Where does B prime have to exist? Somewhere between here and here? Okay. But closer to what? It almost looks like it's 1. We'll do that. There's B prime. Here's the graph of the derivative so far as I see it. And it just checks. Are my slopes positive and is my derivative above the x-axis? Check. As I am getting closer to C, are my derivative values getting closer to 0? If I let this pattern continue, I think I see this happening. And honestly, if I did a better job of sketching this out, it's the green one, there is a point somewhere in here where, okay, we're starting to really accelerate our negative, and then we start flattening out again. See where I'm getting at? So here we're at 0, but then we start getting negative, 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 more negative till right about there. Then we start becoming less negative and turn around and hit towards 0. Which means probably right about there. Oh, gotta be in yellow. The graph has to do that. Look at these. All right, we're negative, we're negative, we're negative. Right there, there's our maximum negative, which is right about there. Because the tangent line slope right about there is as steep as it's going to get, and it starts flattening out. And so that means it's going to start heading back to 0, which means E prime is somewheres right there. It is definitely negative, but it is on its way back to 0. We've talked about points of inflection, haven't we, of graphs?
Yeah.
Where the point of inflection exists is where the minimum of the derivative exists, and there will be that connection. Foreshadowing. Yeah.
Isn't it kind of like make like an S curve as it goes like past like the axis because it's getting like steeper, you know? So
Yeah.
it has to drop faster. So would it be shaped?
Like, are you thinking something like,
Yes.
okay, well, but what you said is actually what it's doing. It's steep, 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 but it's actually slowing down. So it's not getting faster, it's getting, and the rate that okay.
Yeah, but as it comes down below the line, wouldn't it kind of? Because if the slope was -1, the point would be at -1. But then if you go from like D to E, and then it gets to like 3, so then you go down to 3. That would make a curve.
Oh, I I see what you're saying is that I'm probably not going down far enough, but I think in a minute you're gonna disagree with yourself.
Okay.
I think you're gonna say, wait, I see a connection here. But I do agree with something that you're saying. Because my min slope there wasn't even at 1 yet. These slopes, and I think I'm seeing this happen, I think I'm too pronounced there. I think I should be almost straighter. Because I think this needs to dig deeper, because these slopes right here are probably about -3.
Yeah.
Okay, and so I think I see what you're saying. You're saying does it need to, because of how I drew it, and then does it need to do something like that?
Yes.
I'm with you now, and I think what I can alleviate that with is if I drew it a little bit better. Okay, I want to use that. And I think what I would do better with is if it did this. Maybe somewhere's in there. And I think my G prime is too tall or too high. Okay, I think this is fairly inaccurate. I mean, but it really, in reality, here's what an AP multiple choice question on this kind of topic, and yeah, they would have them. They would give you this curve, and then you would have four options, and they would say, which of these graphs could be the derivative graph? And really, what you would want to do is you would say, okay, identify the zeros, and then look at your 4 graphs. Which ones have zeros in the proper location? 2 of them won't. You'll be able to eliminate 2 of them. Then you're going to say, okay, I need to be below the x-axis from there to there. Which one is and which one isn't? All right, so that their accuracy about are we at the exact value? They don't even put an XY grid on it. They just give you an XY axis and don't tell you where they're really at. So really, at this point, I'm just trying to get you to see characteristics, because that's really all they want you to see. Okay, the positive slopes, the derivatives above. We're getting closer to 0, it's decreasing. Okay. And I do have a matching game that we can play where there's cards of the graph and the derivative and the equation of the derivative, and we push it out there and you walk around and match with each other. So I have that, but today is not that day. Okay. Okay. Let's, yeah.
Did you say that we're going to be open circles at the end?
Oh, I did. And I believe there needs to be. And these are the inconsistencies too with AP calculus. If they will never differentiate 2 graphs by open circles versus closed circles. So sometimes they'll close them, and it's a frustrating thing to me. And some books will allow you to do it, and they'll say, well, the left-hand derivative is this, so we'll go ahead and allow it. And so AP Calculus doesn't split hairs on like that multiple choice question. You would have this graph and then the same graph with them filled in and have to make the decision. They'll either fill them in, and so or they'll leave them open. And some people, when you start seeing sample questions, you'll be like, why is that one filled in and this one not? And I'm like, because some people disagree about calculus. It's honest. Like I say, I don't know if I haven't told this class because you guys are brand new. They ran into a question a couple years ago that was such a vague type of thing, and there was so much disagreement out there among people, they threw it out. They got into the grading, and they went, well, it could be this, and it could have been this. They just chucked it. Said, well, we can't ever ask that again because there's too much gray area. So and you'll see that as we get into this stuff. Okay. So let's get into some shortcut rules. Let's use our graphs, and I did that for a reason, because the shortcut graphs, and the shortcuts and the graphs I can tie together. Okay. I'm naturally going to start this with the graph. I'm going to start you with y equals 2. We can graph that, I think. must have taught me something cool. I just gotta remember. He told me that there's a way for me to just insert an XY axis.
It was on the thing.
Yeah, it's on there.
Is it really?
Yeah, we showed it the
Oh, boom, right there. Absolutely cool, okay. But there's y equals 2. Okay? What are the slopes of the tangent line? All right, so we have some visual understanding of what tangent lines look like.
Zero.
So what are they? 0, right? Okay, so if y is 2, y prime equals 0. And I'm gonna jump between notations here a bunch in this little thing, just so that you can see me using them interchangeably. So here I'm in y and y prime notation. Okay? Now, here's something that's cool to me. What if I graph y equals 3?
Still 0.
Still 0. How about y equals -4? Still 0. The derivative of any constant is 0. Which means, and I'll do a couple of things here. So if I did d dx 5, the derivative with respect to x of 5, 0. If
Teachers, pardon the interruption. You would keep all students in your classroom at this time. We're going to have a K-9 inspection. So if you can keep all students in your class and continue to teach, keep all students in your class. We'll let you know when they're available to move again. Please keep all students in your class.
See, things you should never do when they announce a drug dog is like, show someone your bag. I got
Get
lucky.
your drugs out.
One time the
Danny.
drug did find it.
The
Really?
adult,
Yeah.
and then Mr. Hayes was like, so can you guys search your locker? And I was like, I just had a minute.
Funny. Yeah.
Maddie brought her backpack in here to be basically.
Oh, we'll have to let the dog in then.
Only day she's ever brought it in.
Only day she ever brought it in?
Yeah.
Did you know this was happening?
Yeah.
Yes.
I knew it.
Really? It's on video for you just saying that.
Her mom's a board member. She knows.
She
Divorce.
knows. So you knew?
So is yours.
Yeah, duh.
She didn't tell me anything.
Okay, so if f of x is 7, f prime of x is 0. The derivative, so here's rule 1. Derivative with respect to x of a constant is 0 for c equal to a constant. And there's the visual evidence that breaks it up. Okay? And the thing that's awesome about this, don't write this yet. This is just. You remember our limit rules have how I could break and do limits a piece at a time on a function? And we said, hey, we can do the limit of this, plus the limit of this, plus the limit of this, and we could do them as 3 separates. You know what that lets us do is it lets us do the derivative of individual pieces one at a time. It means that if I had this, f of x is 6x to the 5th plus 4x to the 4th minus 3x cubed plus 2x minus 8. That limit rule that lets us break this up means that you can take the derivative of each of these separately. And I bring that up because there's an 8 right there. 8's a constant. I can do the derivative of the constant separately. What will that turn into?
0.
And you see the formation of a shortcut. I didn't have to go through f of x plus h minus f of x all over h with the limit as h goes to 0, because visually I'm getting to see this. Okay? All right. Next rule. Am I good with that? Able to move on? Okay. All right. Let's try the Mason-Russick xy axis. How do I get it to appear? Oh, yeah. Okay. The line that I now want is this. Y equals 2x. So that would be y equals 2x. Yeah. Visually, because now we've set ourselves up and we understand what derivatives look like visually, and we understand that derivatives reference us slopes, and y equals 2x, and we can now, okay, what's the slope of any tangent line to that equation? 2, right? Y equals 2. Okay, so that means that I can come along here and say, okay, I'm going to draw the line. Oh, that even came up in green. That came up in yellow. So y prime is 2. And now you start seeing some coolness to this. Wow, if I just decrease the value of the variable by 1 power, I end up here, right? Or really what happens if I take the power times the constant, I get the slope of the tangent. So that gets us to, and it starts to work for other curves, x squares. Right, so then you start looking at this, x squares. Okay, tell me about all the tangent line slopes up until that point on this curve. Negatives. Tell me about all the tangent lines on that one. Positive. Is if this is a perfect parabola of y equals x squared, are the ones here an exact mirror of the ones there?
Yes.
Mm-hmm. And what is the value of the derivative there? And don't say undefined, because we are smooth, we are 0, and suddenly we have that. So you're telling me that a parabola went to a straight line. 1 power less than 2, y prime is 2x. And there's this connection that happens every single time where the derivative power is always 1 less than the power you started with. And there's this magical connection. And why is it happening? Well, it's happening because remember the f of x plus h, and we canceled out the h? We basically removed 1 power every time we did it. And when we took that power out, we reduced by 1. Okay? So, here it is. Probably the most important rule for derivatives. I'm going to ask her if she's hiding drugs in here. She can come in.
Hey, drug dog's out, you can't be
Got
here.
my wallet.
Okay, you need to stow that in here because the dog won't be in here, or what?
Oh, is there a drug dog coming?
It was on email.
Yeah, we had a funny one because Sophie picked up her little baggie when they heard it and showed everybody, look, I got my stuff with me, so I'm safe.
Yeah.
And Maddie magically brought her backpack.
I had to get this out of Hank's locker. He texted me right away.
Right aboy, Hank.
Get the wallet out of the wallet. All right, have a good one.
Did you need something from her?
Good luck, Miss
No.
Brooke.
Good luck.
Oh, that's right, you're leaving. Good luck.
Good luck.
Sorry.
Good luck.
Good luck.
So how do you release volleyball girls with the drug dog?
Sounds like a really good class.
It is.
You might have to come hang
By the way,
out.
you're on film, so be careful.
Oh, really?
Yeah.
Gee, why are you sitting in a chair?
Should have told her, should have disclaimed her that right away.
Yeah, this Calvin Klein
I
t-shirts.
did it yeah, first.
Okay,
I'm not.
so,
It's because I'm taller. Keep it.
You look like you have really good posture.
Thanks.
Yeah, I thought you were just sitting, but just really straight.
That's what I thought he was doing.
I think she's so fun.
I can't reach the desk if I did that.
okay. The most pertinent and useful differentiation shortcut rule that we've got. And we've got 2 evidences of it, and it is provable. You can prove it. It's not a fun thing to do. You don't need to do it for AP Calculus. The people who do it are the math majors who get into the theorem and the fundamentals behind the calculus, and they start doing a real analytical calculus. We're not an analytical calculus. We're a useful calculus. Our goal in AP Calculus is to create a calculus that is actually useful in explaining the real world. So we don't care about the math that's hidden underneath there that proves this. And really what they do, they're just doing let f of x equal x to the n, and then they're taking the limit as h approaches 0 of x to the n plus h and minus f of x to the n all over h, and it magically comes out to this. And you have to use the binomial theorem, and blah, 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 and it takes a long time. We don't care. What we care is that I had some graphical evidence of why it worked, right? How that constant went to 0 and how that parabola goes to a power of 1 and how that power of 1 went to a power of 0, and we get this rule, okay? I am going to throw this rule to you too so that I can help you out with this. And boy, I don't like it how they are doing it, but we're going to go with their way and we're going to go with my way because we got to pair this. Okay, again, I'm using their notation here. I'll give you my notation after you see their notation. They would like to take the derivative with respect to x of c times u, where c is a constant and u is a differentiable function of x. Very confusing. The other thing that's really problemsome to me in their notation so far is u doesn't have an x and I'm taking the derivative with respect to x, and that they're really lying to you, and they're really jumping you ahead in the world, which I don't care for right now. But here's the rule. d dx of c times u is the same as c times du dx. Basically what they're saying is that you can move constants out front of any rule. And when I do it my way, you'll be like, oh yeah, that makes sense. But this du dx notation is kind of cool because this is the derivative of whatever u was with respect to x. And the du dx is really nice for product rule, chain rule, and quotient rule. Product and quotient you'll get to see today, chain you won't. Okay. So my way is this. Okay. The derivative with respect to x of some constant times a function equals the constant times the derivative of the function, which equals the constant times f prime of x. And when I do examples, it's going to make even better sense. I hope. Okay. Ready for it to actually kind of clarify?
Yeah.
Let's find d dx of 8x to the fourth. Okay? So here's what, in their notation, u is being represented by x to the fourth. Yeah. 8 is the constant. All they're telling us is that the constant can come out front, and I'm going to tell you, you're going to skip this step 99% of the time, but I need you to know the rule. Okay, that means that this is the same as 8 times the derivative with respect to x of x to the fourth. I have not taken the derivative yet. That's why there's still d dx kind of tracking along there with me. This is like instruction. This is like a square root sign. It's like a plus sign. It's saying you have yet to take the derivative of x to the fourth. You need to do it. And then you go back and say, okay, go back up to this power rule. the derivative of an x to a power is equal to the power out front times x to the power reduced by 1. So now what they're saying is this is equal to 8 times the power out front, x to the power minus 1. Or 8, and I'm doing lots of long stuff here, 8 times 4x to the third, or 32x to the third. The short story is this. If you watch my chain of events, I'm allowed to bring the constant out. I've got it down to the derivative of the first rule I gave you, which was the power rule. I actually applied the power rule by subtracting 1 from the power and moving the original power out front. And now I've got coefficients I can multiply of 8 times 4, and 4 minus 1 gave me the 3. The short story is 4 times 8, 32 decreased by 1. Together, those two rules form the most powerful aspect of calculus that we have. Okay? So how you're going to use it is this, okay? If f of x is negative 6x squared, f prime of x is negative 12x to the first. There's the short way. And we're all capable of that. We're all capable of saying 2 times negative 6 is negative 12, x to the second goes to x to the first. Now, be aware, they're not going to write that 1 there. You probably know that, right?
Right.
Okay. So I might say, or negative 12x. Let me run through it longhand. So f prime of x equals negative 6 times the derivative with respect to x of x squared. So I use the constant rule, which equals negative 6 times 2x raised to the 2 minus 1, negative 12x to the first, negative 12x. Okay. Now I got going on this, and I forgot to reference this. One purpose. What does this thing do for me? What is that? That's the derivative. What does the derivative give us when prompted with a number? Slope of a
Of the tangent line.
to the curve at a point. Or
Instantaneous rate.
instantaneous rate of change of the curve at a point. Okay? Okay. We good with this? Okay, I'm cruising now. Let's give you another tool. Sum and difference rule.
So these.
Why is it doing that? Oh, I know why. Okay. By the way, what I would like to do in a second is this derivative. Okay. And now I have the ability. Sum or difference rule. d dx of u plus v, where u and v are two separate functions. Because I was allowed to evaluate limits as individual pieces, and all calculus and all derivatives is a fancy limit, it says, hey, if you want to do the derivative of u plus v, go ahead and do the derivative of u separately plus the derivative of v, which is now going to allow me to do this. All right, f prime of x is. This rule says go ahead and do this separately. Okay, well, do we have a way to do 6x to the fifth? 30x to the fourth plus 16x to the third minus 9x squared plus 2 minus 0.
Should I get rid of the one that doesn't have an x?
Yes, please do. The derivative of a constant is 0. We won't write the 0. Okay, there's f prime. We've got this, which is a really funky, long, complicated polynomial, but we want to know the rate of change of this function at any point. I now have an equation. I can put 1 into there, and I now know what the rate of change of that curve is at the instant that x is 1 or 2 or whatever I plug in. And yeah. Hey, there's the dog, Mr. Ching. Want to bring him in?
Yeah.
Want to do
So if we don't panic.
Yeah, I want to see if it would hit on your bag.
What?
We can test it.
Not your bag, but her bag.
What if that dog likes to do
On Abdul.
Okay, so if, and also there is, there are proofs of all of these in your book, if you're interested, which I doubt you are. All right, so we should be able to get a y prime.
-12.
Okay. -12 x to the third plus 15 x squared minus 2. Yeah? Okay. All right, broken record. There's the curve, there's the derivative. What will the derivative of us tell us?
The rate.
The rate of change from a certain point grams.
Okay. Perfect. All right. Okay. Okay, a thrown rock is modeled by the position function t of x, -16x squared minus 5x plus 3. Okay. That should look like a -1/2 at squared plus v naught t plus h naught type of a setup. So, I want to know where there's a horizontal tangent. What is the slope of a horizontal tangent? 0. Find the derivative, set it equal to 0. You will have the x value of the horizontal tangent. Okay, fair enough. We can get the derivative, right? What would we name it? If we've got t of x, we'll probably call the derivative what?
T prime.
T prime. Okay. So t prime of x is -32 x to the first minus 5. Check that, makes sense? 2 times -16 creates the -32. The power of 2 decreases to 1. 1 times -5 is -5. X to the 0 power, I failed to write it. Remember that x to the 0 power is 1. Right? Anything to the 0 power is 1. So really this is -5 times 1, which is -5. The derivative of the constant of 3 is 0. By the way, remember that in physics, that's the initial height. The initial height always goes away as no effect on the velocity. Does that make sense? That if I throw something from here or throw it from here, The only force acting on it is from my hand and gravity. Doesn't matter the height. The derivative is the velocity of that object at any time. The height doesn't matter, it factors out. Newton's like, that's awesome. And one more is the acceleration, which if you do the derivative of that, you get negative 32, which is the acceleration due to gravity, yeah. Okay, so, but I asked for where there is a horizontal tangent. So that means a horizontal tangent happens when t prime of x equals 0. So then I come back and say 0 equals negative 32x minus 5. So that means 5 equals negative 32x. So x is negative 5/32. And maybe this is a bad model because that would be time, and before time happens it maxed out. That's fine. It means I threw the rock downward actually, with no arc to it at all. But, horizontal tangent. So, wait a minute.
So that's the maximum height.
It's what?
Maximum height.
You got it. Did I just locate the max value of that parabola?
Yes.
Yeah. Negative 5/32 is the max. There's t of x has a max at negative 5/32. The significance, let's say this. Negative 5/32 is the max and x value of the vertex of the function t of x. What's that? Well, because I know some stuff about parent functions and the leading coefficient of the x squared is negative, so I know it's a parabola that's going like this. It's either the min or the max, right? Because it's a horizontal tangent, which means it either came down, hit that spot, and turned around.
And then you know
or-
where to turn it down, okay.
Yeah, and I knew where that's down. Now, there is a way where we will do a test later on here and test the value of the derivative on either side and see if it's positive or negative. And that will tell us whether we're increasing and decreasing, and then we would know if it's a max or a min. Okay, 2 more rules in 20 minutes. Now, let me be honest, this really isn't a problem because after you see the product rule, when you see something like this, you're probably going to multiply it out and use the other rules, right? Because that would be x squared minus x minus 6, 2x minus 1, done. But I want to show you the product rule because then I can get into square roots and trig and all sorts of good stuff. And the product rule works like this. Product means what, by the way?
Multiplication.
Multiplication. Oh, I got 2 functions multiplied together. Okay, I'm going to write it in a whole bunch of notations. Here's my notation, not your book notation. H of x equals f of x times g of x, if. Then h prime of x equals f of x times g prime of x plus g of x times f prime of x. To me, that's the most useful version of the product rule. So look what it does. It takes the first function as is, multiplied by the derivative of the second function, plus the second function as is, multiplied by the derivative of the first function. So did everybody get their turn to have a derivative taken? Yeah, I got a g prime and an f prime. Did everybody not have a turn in getting their derivative taken? Yeah. Okay. That's my notation. Here's theirs. Remember, we're talking the same thing. Newton, Leibniz. Newton, Leibniz. Newton like primes, Leibniz likes DDX. It's two guys making up the same math at the same time in different parts of the world, and two different types of notations that are both useful in their own right, so we haven't got rid of either of them. Okay, let's check it out. Two functions, u and v, f of x and g of x. Don't take the derivative of the first one. So regular f of x, regular u. Do take the derivative of the second one, g prime of x, dv dx, the derivative of v with respect to x. Plus, don't take the derivative of the second one, there's v, times, do take the derivative of the first one, f prime, or the derivative of u with respect to x. You do need to understand them in both ways. Never know how it's going to get approached to you. Let's not use my example. Let's use something that would be more relevant to it. Like, let's let f of x be x to the fifth minus 9x times x cubed plus 2x squared. Certainly we could multiply them out. It's really not that difficult. What's the first function going to be? What's the u or the f of x? X to the fifth minus 9x. What's the second function then?
X cubed plus 2.
All right, so f prime of x.
Teachers, I'd like to give you all clear signs this time, as well as release the volleyball girls headed to Butte Central. Wish you lots of luck. Play hard and have fun.
Good luck, kids. Thank you.
Oh, there's a lot of spelling on the street.
Okay, so here's my setup. And I strongly encourage right now that we write out this setup and we don't try to go right to the derivative here, because as things get more complex, we want to, basically the product rule needs to be like second nature to us. And so the more I have you write it out, but let's just talk through it. First function times d dx of the second. I have not applied a derivative rule yet, right? I haven't done the derivative of x cubed plus 2x squared. This is still instruction that says, please do so. Right? Just like it says, please take a square root, or please take the sine of something. Once I do the derivative of it, this d dx will mysteriously fade away. Plus, you see how these two functions are the same. One's going to get the derivative taken of it. This one it's not. Times the derivative of the first that I left alone in the front. Okay? So now, I haven't even checked this. Has my battery died?
If your battery died, it doesn't say what you recorded.
You're right. Hour 3. We're good. We're rolling.
Can you even see that board?
Yeah. All right. So here we go. X to the fifth minus 9x times. What's the derivative of x to the third plus 2x squared?
3x squared plus 2x.
Try again. 3x squared plus
4x.
4x. Plus x cubed plus 2x squared. d dx of x to the fifth minus 9x. 5x to the fourth minus 9. That's it. That's my derivative. Leave it. Don't get caught up in simplifying stuff. Because, I mean, could you multiply this all out? You bet you could. But if the whole purpose of f prime of x is to tell me what the slope is at a certain spot, and say I wanted the slope at 0, could you go through and put 0 into every x and get a numeric value?
Yeah, 0.
Okay. Don't oversimplify stuff unless you absolutely have to. That's a derivative. It's good. It's clean. It's usable. We have usable math. That's all we need. Okay? Let me change gears on you in this next 2 minutes. F of x is root x. My rules only work for powers. Square root of x in terms of a power is what? X to the half. All right. Well, we can rewrite things so that we can use our rules. So this is the same as f of x is x to the half power. And I know that they introduced this, or I introduced this for integer powers. I'm here to tell you it doesn't matter. They can be fractions, they can be negative, they can be positive. It works the same no matter what. So if f of x is x to the 1/2, f prime of x, 1/2 goes out front, x to the negative half. Because what's 1/2 subtract 1? And I'm going to write it in as f 1/2 minus 1, or 1/2 x to the minus half. I will say this, AP never allows you to leave an exponent negative. Well, no, I take that back. Written response, yeah, you could be done. Multiple choice will never leave them like that. How do I make x to the half positive?
You put it in the denominator.
Put it in the denominator. So f prime of x is in reality 1 over 2x to the half, which is in reality 2 over square root of x. Cool, so the derivative of root x is 1 over 2 root x.
Can you have a square root of 1?
Yeah. We will allow you to have a square root in the denominator. We will not rationalize something.
Even in multiple choice?
Yep. You know how they get around that? They'll ask you to find the value of f prime at 4. And so then their answers are just going to be numeric instead of a function. And so now you go back and put 4 in for x, and you get 1/4. Okay. That good? Last rule of the day. The quotient rule. I'll do it their way first. Question, if Miss Quinn sent me a text in the middle of this videoing and it's sitting on the screen, it's not actually in the video. Solid.
Are you worried?
Nope. It was a very innocent one. Nothing about a costume or anything. All right, the quotient rule. The quotient rule is usually the rule that people dislike. Okay. So the derivative with respect to x of u over v goes this way. Let me make sure I do it the way they want to do it. It's going to go denominator times the derivative of the numerator minus numerator times the derivative of the denominator with respect to x all over the denominator. Oh, you're kidding me. All over the denominator squared. So, and order matters. Denominator times derivative of numerator minus, that's what makes the order matter, minus numerator times derivative of denominator all over the denominator squared. Okay? In my notation, Here it is in my notation. Denominator times derivative of numerator minus numerator times denominator of, or times derivative of denominator all over denominator squared. Okay, so that means, let's do this. There's a nice rational function, x squared minus 3 over x to the 4th plus 1. So we reference that and say, oh, quotient rule it is. So f prime of x equals, and so the quotient rule says, denominator, well that's x to the 4th plus 1. So that's going to be x to the 4th plus 1 times d dx of x squared minus 3, because that's the derivative of the numerator, minus the numerator times the derivative with respect to x of the denominator, all of this over regular denominator quantity squared. And you think it's a shortcut, and it is a shortcut. Remember the other way to do this, the limit as f of x plus h, or as x goes to 0, of f of x plus h minus f of x all over h. Well, I bet you don't want to be at x plus h quantity squared minus 3 over x plus h quantity to the 4th plus 1 minus x squared minus 3 over x to the 4th plus 1 all over h, and simplifying that out to get h to cancel. Okay? You can do it that way, but it's just amazing that this rule works out. All right, let me finish this up. That'll finish us up. So this is going to be x to the 4th plus 1 times 2x, right? 2x?
Yes.
Where'd the 3 go?
Oh wait.
Because
It doesn't have
it's a
a constant.
constant, okay? I know, and I need us to know math terms. That's one of the things they actually want is to know math terms. Okay, derivative of x to the 4th?
X, 4x to the 3rd.
4x to the 3rd. Nothing in the bottom changes. Okay, that's a solid derivative. I will forewarn you, this is a good opportunity to say, okay, multiple choice, it probably doesn't look like that. They probably do this. Distribute, so it's going to be 2x to the 5th plus 2x minus 4x to the 5th plus 12x to the 3rd. All over x to the 4th plus 1 squared. Do we have like terms that we can combine?
Yep.
Sure we do. Now it goes to negative 2x to the 5th plus 12x cubed plus 2x all over x to the 4th plus 1 squared. There's f prime of x. One more time.
Would it choose to separate out the two, like x to the 4th plus 1 times x to the 4th plus 1, and then do that all out?
If this factors into an x to the 4th plus 1, they would do that so they could cancel. But it very rarely would happen. Okay, yeah.
Why are we not doing anything to the bottom?
Like multiplying it out?
Yeah, the denominator.
Yeah. Well, the first off, the quotient rule just says leave it alone.
Just leave it.
Okay. But
Could you?
multiply it out, absolutely. But you
Well-
can't take the derivative of it. You're gonna leave
You
it.
can't take that side of this side.
Yeah, you don't, yeah, nope.
No.
Okay. You are almost fully qualified to do every derivative in the world. You don't know how to do trig stuff, and you don't know how to do chain rule stuff. That's fine. That's the next time. Like I say, I will not be here Thursday. What's gonna happen Thursday is basically you're going, and I'm not assigning anything right now for you till Thursday, but when you come in, whoever is in here, you're gonna basically have a page of functions and the request of finding f prime. What's that? Nothing. Okay, that's what we're doing Thursday. We're doing that worksheet.